So today we are basically going to talk about the last topic basically of Unit 1, which is topic 2, and we'll cover everything related to topic 2. Okay. At first, let's move on to the first part, which we need to talk about what is electronic configuration, the base part of this whole topic here. All right. Okay. Uh, First of all, we learned this a long time back, during our preschool years, and when we were not in grade 10 or 9, when we were back in 7 and 8, that electrons, the most simplest idea of our uh, uh, you know about atoms is what, that electrons basically rapidly move around the nucleus in energy shells. That's what we used to know, right? For example, this was the nucleus, and around the nucleus there were some circular shapes, and within these circular shapes the electrons exist. At least that's what we know from our pre A level you know knowledge, isn't it, Mohideen? Am I right? For example,
Yes, sir.
281, what does this indicate? That means the second shell can occupy up to 2 electrons. The first one can occupy up to 2 electrons. The second one can occupy up to 8 electrons max, while the third one can occupy up to 1 electron. Not 1 electron, to be honest, it can occupy up to 8 electrons max, but here we have 1. So whatever is this, like this arrangement of electrons, or the arrangement or the way in which these numbers are arranged, this basically represents electronic configuration. All right. Now, what are energy shells or energy levels? We can say as energy shell or energy level, whatever you say. These are basically circular areas or regions where electrons exist within the atomic structure. All right, and there are different energy levels, meaning that each and every energy level, the energy of each and every energy shell is not same. Say for instance, the most innermost shell compared to the most outermost shell. All right, the innermost shell has the lowest energy. All right, if I show you in a deep way, let me show. If I show it here, that's the nucleus. Okay, so what we're trying to say is that this is the energy possessed by the first energy shell is this, and the energy possessed by the second energy shell is this. All right. So E2 is greater than E1. All right. So as you keep on energy, the shell keep on adding the number of shell, and what is happening? The whatever shell you are adding to the whole structure, that energy shell will definitely have a higher energy than its predecessors. Am I clear? Sarah, did you understand? This is what the whole electronic configuration thing is about. And since the electrons are present within these shells or regions, so they are going to possess the same energy, just like just like these shells possess. For example, let's say E1 is equal to 400. So each and every electron present in this, sorry, E1 is equal to 400. So this electron present in this shell will also have the same, energy. Did you understand? Hello, Sarah, do you understand?
Okay.
Okay, so that's how it happens basically. Now there is a thing called ground state and excited state. Electrons, whenever they absorb energy, they tend to move from their ground state to their excited state. Now we don't know which one is the ground state or energy state. It kind of depends on the electron which basically absorbs the energy. Say for instance, externally an energy is provided. It could be via light or anything, something like that. But let's say externally energy is provided, and let's say this electron right here took absorb this energy. So what happens? It does not. So the electron is obviously in the first shell. So this is the ground state. All right. The electron which absorbs the energy, the electron in which the shell it is present, that shell is known as ground state. All right. Now it will absorb the energy, and now it move on to shell which has a greater energy than its ground state. So the shell which has a greater energy than its ground state, and where the electron goes due to the absorption energy, that shell is known as what? Excited state. Am I clear? So after it moves there, it does not stay there for a long period of time. It then returns back again. Now, when it returns back, all right, when it returns back again, it releases or emits energy in the form of waves. All right. So always remember that most of the time, and it's a clear concept. Always try to remember that the ground states are the inner shells, while the outer shells are known as the excited states. Simply because the electrons, most of the time, the electrons present in the inner shells absorb the energy and tend to go, above to a higher energy shell. Do you understand? Sarah, especially, I'm talking.
Mhm.
Okay. So this is how the whole concept of electronic configuration is. Now, that was a simplified version of 281, which we just saw, and which we basically acquired during our pre-IGCSE, from our pre-IGCSE knowledge. Now we are going to go into AS level, where the electronic configurations are discussed in more advanced format. Here you have orbitals. Orbitals are what? Orbitals are basically subshells. Subshells contain one or more atomic orbitals. What they're trying to say is that, just remember one thing, that that is, energy shell is greater than orbital. All right, and orbital is greater than subshell. Okay, what is this trend? This is the what? Size and priority. This means what? That an energy shell, a quantum energy shell, or what we have which we have discussed here below, these are known as quantum energy shells. So a quantum energy shell will be greater in size compared to an orbital, which will obviously greater in length compared to a subshell. That means a quantum energy shell consists of both the orbital and subshell within its structure, and within orbital we have subshell. All right, I hope you understand. Okay. Now, orbitals exist as specific energy levels, and electrons can only be found at these specific, levels, not in between them. Okay, I think I made a mistake. Maybe I did the opposite. It's typically subshell and then orbital. Sorry, I made a mistake. So what I'm trying to say is that quantum energy shells contain subshell within their structure, while subshells consists of orbitals. Yes. Now, there are many types of orbitals. We need to understand that. Well, there are four types basically: S, P, D, F. All right. S orbital, P orbital, D orbital, and F orbital present within the different subshells, which are present or spreaded in different quantum energy shells. What are quantum energy shells? We have just seen these are quantum energy shells, the sky colored things that you see down here. These are just 2D simplified structure, but in reality it is much more complicated. What do you think? But just for simplicity and for understanding clearly, we drew the energy, quantum energy shells like this. All right, and always try to remember this trend. Now, there are four types of orbitals. You have S, P, D, F. There are, S, obviously, there is only one type of S orbital. There are three types of P orbitals, five types of D orbital, and seven types of F orbital. Now, always try to remember one thing, that one orbital can consist of maximum two electrons, not more than that. So that is how they basically calculated how many electrons that all the five orbitals can you know handle. So since there is only one type of s orbital, so obviously two electrons, three times two, 6, d 10, f 14. In the future, as I move on with the lecture, you will understand more what I'm trying to mean here. Now, these orbitals have specific 3D shapes. Now, what are these 3D shapes? If I talk about this one, s orbitals, the s orbitals are spherical in shape. The size of the s orbitals increases with increasing shell number. This is an example of an s orbital, as you can clearly see. This is spherical. You can see that. This is spherical. You can see that. All right. It can be normally drawn as like this, but you can also draw it like this as well if you want. So it's a spherical shape, and you have to remember this, that the size of the s orbital increases with increasing shell number. So this basically means that the s orbital of the third quantum shell is bigger than the s orbital of the first quantum shell. What they're trying to say is that these are quantum shells, right? So let's say the first one is n is equal to 1, this is n is equal to 2, and that is n is equal to 3. All right, so they're trying to say is pretty simple, that the s orbital present in the third quantum shell has a greater size compared to the s orbital present in the first quantum shell. That is what they're trying to say. Nothing else. So as the n value increases, the size of the s orbitals also increases, but their shape remains constant. Just remember that. And each orbital can consist up to 2 electrons. All right. Now d orbitals, obviously there are three types of sorry, p orbitals. There are three types of p orbitals, and now they are dumbbell shaped. Well, this is how they are normally drawn. This, second, third, this is the three p orbitals. As you can see, it's just that the orientation is different. As you can see clearly that this basically occupies x prime axis, this one occupies y prime axis, while this one occupies the z prime axis. All right, now what are orbitals? Basically, within the orbitals are basically regions where there is 89% probability. I mean, this is a value basically what the chemists have found, not me, of having electrons to exist. So what chemists are trying to say, or what physicists are trying to say, is that orbitals are basically regions of different shape, or no, different size and shapes, where there is 89 to 90% probability of having electrons within an atom. Okay, that is what orbitals are. These are basically just regions where there is 100% charge. That means the electron might be present here or here or here. There is a very less probability that the electron will be present outside the orbital. There is higher probability that the electron will be present within this colored region. All right, and this colored region is spherical. That's why it's s orbital. So depending on the shape, the orbitals have been classified. Did you understand, Sarah?
Yeah.
Okay. So that's how it goes basically. So as you can clearly see that, look, so this is the shell, or the quantum, this is the quantum shell. This is like a Venn diagram. All right. So what I have drawn here, what I have written here, this priority group, they have just shown in the Venn diagram. As you can clearly see that quantum shell contains orbital and subshell both, but within subshell the orbitals are present. All right, this is very important to remember. So we know that shell is greater than subshell, which is obviously greater than the orbitals. So I guess this picture basically summarizes everything what I'm trying to explain. Okay, now one thing you need to remember, that is, what are these numbers right here? 2p, 2p. Now this is obviously 2px, 2py, 2pz. Now what is 2? 2 here represents n number. This is the value of n. All right, that what does this represent? This basically means that these p orbitals are present n equal to 2. That means in the second quantum shell. All right, and this is also the same thing here, n is equal to 2. That means it's present in the second quantum shell, nothing else. All right, and why did I give px, py, pz? Because of the orientation. I guess you understood. Now, filling the orbitals. Remember one thing, electrons can be imagined as small spinning charges which rotate around their own axis, either in clockwise or anti-clockwise direction. Now, this is how electrons are present within an orbital. In the orbital could be spherical, or the orbital could be, could be like, dumbbell shape, whatever you name it. But within these p and s orbital, the electrons will be present in opposite spins. This is very important. That means if one is rotating in clockwise, the other one must be rotating in anti-clockwise in order to, what does it do basically? The spin of the electron is represented by its direction, obviously this direction. The spin creates a tiny magnetic field within the ns pole pointing up or down. So what happens is that, remember one thing, electrons with the same spin repel each other, which is also called spin pair repulsion. Therefore, electrons will occupy separate orbitals in the same shuttle first to minimize this repulsion and have their spin in the same direction. They will then pair up with the second electron being added to the first p orbital with its spin to the opposite direction. So what they're trying to simply say that two electrons cannot have the two electrons occupying the same orbital, should not have the same spin, because if they have the same spin, the magnetic field which is created by these spins, they will just simply add up. Say for instance, this is also in clockwise, and instead of this anti-clockwise, let's say this is also in clockwise. So now this is not possible, because the magnetic field produced by this spin and the magnetic field produced by this spin, these two magnetic field will add up and produce a greater magnetic field, resultant magnetic field, which will not, which will basically create repulsion between these two electrons, and so they cannot occupy the same space together. So that is why it's very important the spins are, in the, the direction, the spin direction is in the opposite for both electrons. One should be in anti and another should be in clock, so that the spin produced, cancels out each other, and so the magnetic field produced cancels out each other, and the repulsion basically, gets minimized, and they can basically occupy the same space. I hope you understood this. Now, this is known as what? Who proposed this whole theory was known as Hund, and that is why after his death, the theory was basically known as Hund's rule. All right, did you understand, Sarah?
Yeah.
All right. Now, Hund's rule is obviously very important. Uh, is this Hund's rule? Oh, sorry, not Hund's rule. Sorry, I made a mistake. Hund's rule is something else. This is known as the Pauli exclusion principle. Pauli exclusion principle. I made the opposite mistake. Sorry. No, what I'm trying to say, what I just discussed here is known as the Pauli exclusion principle. As you can see, can only hold two electrons, and they have, opposite spin. This is known as Pauli exclusion principle, because obviously scientist Pauli discovered it, and after his death, under his honorary, this principle or theory was made. Now, what is Hund's rule? Check this out. Uh, let's say there are what we know, there are three p orbitals, right? Let's say this is px, py, and this is pz. So what they're trying to say now, we know what the principal quantum number indicates the energy level of a particular shell, but also indicates the energy of the electrons in that shell. So a 2p electron is in the second shell, and therefore has an energy corresponding to n is equal to 2. So remember one thing, that always remember one thing, that is what? That is, this px is greater than py and greater than pz. No, actually, I made the opposite. This is the energy trend. All right. As you go this way, the energy tends to increase. Now, what does the Hund's rule say? The Hund's rule basically states that not two electrons will, together occupy an orbital. Rather than that, at first, one electron will occupy each of the three orbital consecutively, and after that, the other, three electrons will occupy like this. That means what I'm trying to say is that, say for instance, there are three p, we know that there are three p orbitals, right? Electrons are not going to get, you know like at first px won't get, occupied by the two electrons, and then py will get occupied, not like this. According to Hull's rule, px, py, pz will receive, each of these will receive one electron consecutively, and after that, they will, if there is any other electron, you know they will get occupied like this. Did you understand, Sarah? This is known as the Hund's rule. That means what they're trying to say, according to Hund's rule, the lower energy orbitals get filled up before the higher ones. Did you understand what I'm trying to say?
ভাইয়া এটা কি শুধু পি অরবিটালস এর ক্ষেত্রে?
Sorry.
এটা কি শুধু পি অরবিটালস এর
No, no, no.
ক্ষেত্রে?
It is for every type of orbital. This is just an example. I have just used p orbital as an example. It could be
আমি
for
এটা
d orbital
বুঝলাম,
as well. Did you
আমি এটা
understand?
বুঝলাম
What
না,
didn't you understand?
যে এই সাইন গুলো কিভাবে কিভাবে দিচ্ছে,
Sorry.
মানে এটা ওয়ান সাইন গুলো কিভাবে দিচ্ছে, মানে
No, these are not one sign. These are electrons.
আচ্ছা, তো
These
এটা
are
কিসের উপর নির্ভর করে দেওয়া হচ্ছে?
it is depending on the Hund's rule. And what is the Hund's rule? The lower energy orbitals get filled up before the higher ones. Didn't I show you the trend right here? What? Pz has the higher energy than py, and py than px. Did you understand? So did you notice something? Yeah, at first pz is not being occupied. At first px is getting occupied, then py, then pz. Did you understand?
হ্যাঁ, আর পরে যে
then
আবার
uh,
এসব
then what? Then okay, let's say I'll show you something. If I show you an electronic configuration, then you might understand. Mohideen, can you please tell me what is the electronic configuration of sodium? 281, right?
Yeah.
Look, Sarah, 1s2, 2s2. How many electrons are there? 11 electrons, right? So we now need to write it in the quantum energy shell format. Not now. We are not. We will not write write in the IGCC format. Look at this. 1s2, 2s2. 4 electrons gone. How many electrons left? 1s2, 2s2. 2p 4. More 7 electrons required. 2p6 3s1. Now look here. Obviously, now you have to remember one thing, which is that this is important. If I show you, I was going to show you, to be honest. Uh, Check this out. N is equal to 1 has only one orbital. Remember that. N is equal to 2 has, you know, two orbitals. Uh, and always remember another thing. N is equal to 3 has, sorry, forget 4s, has 3 orbitals, while N is equal to 4 has 2 orbitals. Do you understand? Oh, actually, there is 4d as well and 4f. So that basically sums up this 4 orbitals. It has 3 orbitals, and n is equal to 2. That means the second quantum shell has 2 orbitals. This is important to remember, because if you can remember this, then you can basically develop the electronic configuration or the electronic configuration format. Did you understand what I'm trying to say? Like, you have to remember this. Hello?
না, সেটা বুঝি নাই।
What part you did not understand? Please tell me.
ডায়াগ্রামটা বহুত কনফিউজিং লাগতেছে আমার কাছে।
What is the
এটা একটু
confusing
আবার
thing?
এক্সপ্লেইন করবে?
Acha, in n is equal to 1, there is only one orbital. I'm trying to say, in the first quantum shell, there is only one orbital. In the second quantum shell, there are two orbitals. We know there is only one type of s orbital, and we know there are three types of s. There are three p orbitals, isn't it? Little while ago we
হুম,
saw. Little while ago we saw that, right?
হুম,
Didn't we see that there are three p orbitals, right? And the third quantum shell can have 3s, 3p, 3d. That means the third quantum shell can have three types of p orbitals. Am I clear? And depending on if it's p, then obviously there will be three subshells. And if it's d, then obviously how many, one, two, three, four, five subshells. And obviously again, to the fourth quantum shell, we again tomar 4s, 4p, 4d, 4f. Mane, do you notice something that as the n value increases, the capacity of what's it called, the capacity of handling orbitals also increases. Did you notice something? Like, as the n value is increasing, the number of orbitals is increasing. Did you
হুম,
understand? Isn't it? So this is very important to understand. তো এই জিনিসটা যদি মনে রাখতে পারো, or if you can memorize this, then obviously in order to write the electronic configuration anything, you can do it. And always remember, this is the sequence. Okay, you start from n is equal to 1 2 3. Now depending on the number of electrons present, we are going to stop. Say for instance, sodium right here, 281. So obviously, what is there? There are 281, 11 electrons, right? Yes or no? 11 electrons, isn't it? So we know what? S orbital, okay, in n is equal to 1. In n is equal to 1, there is only one orbital, isn't it? So obviously, uh, 2 electrons gone there. Then we know, then we move on to n is equal to 2, because obviously n is equal to 1 cannot have any more orbitals. So we go to the second quantum shell where we know 2s and 2p. That means two different types of two different types of orbitals are there. And among these orbitals, the s orbital has only obviously one subshell, and the p orbital has how many? Three subshell, isn't it? So as you can see, this is
So
where,
এখানে পাওয়ার কত কি রিপ্রেজেন্ট করতেছে?
oh, the power basically represents the number of electrons.
মানে টোটাল নাম্বার অফ ইলেকট্রনস ওই অরবিটালটা,
Sorry.
ওই অরবিটালটা টোটাল নাম্বার অফ
Yes,
ইলেকট্রনস এখানে।
yes, exactly. The power basically represents the number of electrons in that orbital, specific orbital. And we know in p orbital is how many subshell? Three subshell, isn't it? And s orbital is only one subshell, right? So on and so forth. So এখন check this out. 226, how many? 10 electrons gone. We know that 281, 11 electrons are there in sodium. So the last electron, obviously we can't, we need to go to the third quantum shell, n is equal to 3, and which the first one is obviously 3s1. So s orbital is only one subshell, so one electron. So this is the electronic configuration of sodium in the what? What's it called? Uh, Quantum shell format. Did you understand?
হ্যাঁ হ্যাঁ।
Now, what is Hund's rule and Pauli exclusion principle? This is very important. Well, Pauli exclusion principle, I told you. What did I tell you? Like in a subshell, two electrons cannot occupy by having the same spin. But by the way, remember one thing. If both of the arrow sign are represented upwards, or if the direction is upward, this basically represents the electrons present are in the same spin, which is obviously not possible. So this is what the Pauli exclusion principle states: the other electron must have opposite spin. That means the direction should be downward. Did you understand the significance of the direction of the arrow? I hope you did. And what is the Hund's rule? Did you understand?
ধর স্পিন যদি সেম ডিরেকশনে হওয়া পসিবল না হয় তাহলে এটা
Didn't I
ইয়া কেন?
explain it a little while back? I explained you, didn't I?
হ্যাঁ হ্যাঁ, সেম ডিরেকশনে যদি এটা হওয়া পসিবল না তাহলে এটা দিয়ে লাভ কি? লাইক এটা ইটস নট দ্যাট
Labo.
ইম্পর্টেন্ট।
What do you mean by it's not that important?
ইম্পর্টেন্ট তো হয় না, লাইক যদি সেম ডিরেকশনে স্পিন না হয়, স্পিন তো আমার ডিফারেন্ট ডিরেকশনে প্রতিবার হচ্ছে।
Yes, if it is in same direction, the magnetic fields produced by these spins in each of these electrons won't what? Eliminate. And if the magnetic fields do not eliminate, they will repel each other. And if they repel each other, do you think they will be able to occupy the same space together? No, right? Did you understand what I'm trying to say?
হ্যাঁ বুঝছি।
That's what I'm trying to say. That is why it's highly important that both of them are, both of them have the opposite spin, so that their magnetic fields get eliminated and they don't they don't experience repulsion. Okay, this is what Pauli exclusion principle teaches us. Now, what is Hund's rule? What I was trying to say. Now, you have understood the electronic configuration, right? Now, Hund's rule basically, shows you the way of filling up the subshells. Say, for instance, you know, P and look at how it works. We want to fill up these orbitals, right? At first, the s orbitals will get filled up. All right. Obviously, at first the s orbitals will get filled up like this. At first, one electron gone, then another electron comes. Actually, yeah, sorry, not like this. Let me tell you from the first. So, how will you fill up these orbitals? At first, you'll provide one electron according to Hund's rule, like this, and then the second electron will be provided. Now we can't give another electron here because obviously it kind of fulfills our requirement. That's why this is how you fill up the orbitals. What does Hund's rule say? The Hund's rule basically says the lower energy orbitals get filled up first before the higher energy ones get filled up. Did you understand? Did you notice something, that I did not start filling up the orbitals from the third quantum shell? I started filling up the orbitals from the first quantum shell. All right, because they are of the lower energy. Did you understand what is Hund's rule?
হুম।
All right, and another thing that is very important, check this out. Like when you fill up the, did you notice another thing, that when I filled up at first I gave one electron in each of the orbital, I did not do this. I did not do this. Did I? I did not do this. At first, each of the orbital will fill up one orbital like this, and then the second electron will be added. All right, this is what Hertz rules say, that each orbit, the lower energy orbitals will occupy one electron consecutively before the second electron is added. All right, this is what the Hertz rule states. I hope you understood. And this is, I guess, the chart is understandable. And yeah, this is what it is. You can see here what it represents. I was going to say it from before, but this is what it represents, as you can see. So I think you can understand that a p orbital can occupy maximum six electrons. S obviously two. D has four. We know that D has four. If it's 3D, so obviously how many subshell? 1 2 3 4, right? So 1 2 3 4 5 6 7 8, maximum 8 electrons. Sorry, 1 2 3 4 5 6. There are five orbitals. I forgot. There, so maximum how many? 10. Did you understand? This is the number of electrons, Sarah. All right. So this is what it happens. Another thing, the full electronic configuration describes the arrangement of all the electrons from the 1s subshell up. The shorthand electronic configuration includes using the symbol of the nearest precedable noble gas to account for however many electrons in that noble gas are. Okay, if I give you an example, let's say potassium. Look at this electronic configuration right here. Do you see this? 1s2. Oh, how many electrons are there in potassium? We can clearly see. We can see what 1s2, 2s2, 56. So that's 10, 12, 18. So we can see there are 19 electrons. Right. Now we can represent this part as argon. Why? Because argon's electronic configuration is equal to this. That means argon has 18 electrons. Did you get what I mean? That means sometimes you can also write the electronic configuration, the shortened electronic configuration of, potassium and other elements like this, where you place, where you basically up to 3p6 you can represent using this argon notation. Did you understand, Sarah, Moidin, what I'm trying to say?
Yes.
Okay, all right. Now, this is very important. Chemistry is all about exceptions, we know that. And also the color part is also very crucial. So exception is exception. You have to remember the exception, which is obviously chromium and copper. They have the following electron configurations, which are different to what you may expect. See, you should expect this, right? You should expect this. Say for instance, what chromium is how many? 18 electrons, and then if you add 5, so obviously 23, so 24 electrons. Chromium is how many? I guess 23. There are 24 electrons, and copper has obviously 18, 28, 29 electrons. Now, according to Hund's rule, you should expect this. They don't actually follow. They don't follow traditional Hund's rule. These are the only two elements in our electronic configuration. Why? If I show you nicely, check this out. Argon. All right, I don't have to show this. Now check out 3D and 4s. 3D and 4s. We know d orbital is how many? How many subshell? Sarah, how many subshell? 4 or 5? 5 subshell, isn't it?
Right.
And it is one orbital. Now here 18 electrons have been done. So obviously there are how many? 24, right? So the rest 5, 6 electrons. So how will you accommodate the 6 electrons? Now according to Horn's rule, what do you think should happen? 1, 2, 3, 4, 5, and then 6, isn't it? That means 3d5, 4s1. This is what should have been happening, but unfortunately this does not happen. You see, this is what happens. 3d4, 4s2 happen. Sorry, what's it called? Uh, this is what happens. I think I made a mistake. Sorry. This is what it should be happening. 1 minute. Did I make a mistake? 1, 2, 3, 4. are therefore hmm, hmm, 1 minute. Okay, I'll explain this a little while later. No problem. Meanwhile, join again. The meeting link. The meeting is finishing. I'm sending you a new link again. 1 minute.